I welcome you once again for this series of lectures on discrete time Fourier transform, discrete Fourier transform and fast Fourier transform. In the previous series of lectures, we have talked about discrete time Fourier transform, which was used for finding out the frequency domain information of discrete time aperiodic signals. We had seen one thing, that the discrete time Fourier transform is continuous in nature. Hence, it is not of that practical importance, because practically we are processing the signals which are digital or discrete time, and we cannot process continuous time signals. Therefore, there is a need of another transform which is called as discrete Fourier transform. So, summarizing this, we had already seen that we got the discrete time Fourier transform, which is the frequency domain representation of discrete time aperiodic signal, but the nature of DTFT is continuous. So in order to make this DTFT discrete, we have to sample it in the frequency domain. So by sampling the discrete time Fourier transform, we get a transform which is called as a discrete Fourier transform. So DFT is different than DTFT. The nature of DFT is discrete. In nature it is discrete. Therefore, this, since it is discrete, we can process it with the computer, we can store it on the computer, we can process it on a computer, and there are a set of algorithms which are available for computing the discrete Fourier transform, which is called as the fast Fourier transform algorithms. Hence, due to availability of these fast Fourier transform algorithms to compute DFT, this has become the most popular tool for processing the discrete time signals in the frequency domain. So this is how we get a transform by sampling DTFT, discrete time Fourier transform, in the frequency domain. In order to make that transform of practical importance, uh, and store it on a computer, process it on a computer, and we can have a set of fast algorithms to compute the DFT. So in short, we have to remember that discrete Fourier transform is obtained by sampling discrete time Fourier transform in the frequency domain. Discrete time Fourier transform is continuous in nature, whereas discrete Fourier transform is discrete in nature. Another thing is, there is a set of algorithms which are available to compute DFT. These algorithms are called as fast Fourier transform algorithms. So FFT is not a transform, it is a set of algorithms for computing DFT. So DFT is the main transform, and we will talk about FFT more later in this talk. So in short, we can see that in order to make discrete time Fourier transform of practical importance, we are sampling this in the frequency domain, and we get a transform which we call it as a discrete Fourier transform. We can write the equation for DTFT for finite number of samples. If we consider the length of the sequence x of n as of length n, then we can write the equation of DTFT which we had seen in the previous lectures. Now this is for the finite sequence. Okay. Now if we want to make this continuous variable omega, which is continuous in nature, discrete, we can sample it with this. We can sample it into k samples by using this formula. So we can substitute here omega as equal to 2 pi upon n, where k will be integer from 0, 1, 2, 3 up to n minus 1. So in this way, by taking the Fourier by sampling the continuous variable into discrete, we get a transform which we denoted by x of k. So x of k is called as the DFT of x of n. So DFT is denoted by the symbol x of k, and DTFT is denoted by the symbol x of e raised to j omega. So this is DTFT and this is DFT of the sequence x of n. So DFT is the formula for DFT is summation n equal to 0 to n minus 1. It is for a finite sequence. Here we are not having from minus infinity to plus infinity, just like we had the case for discrete time Fourier transform, because here we are considering only a finite duration sequence. Okay, so the duration of the sequence is of length n. That's why this formula is modified from n equal to 0 to n minus 1. and in place of e raised to minus j omega n we are having this e raised to minus j 2 pi n k upon capital N. So the value of k ranges from 0 to n minus 1, where capital N is the length of the sequence, is called n. The capital N denotes the length of the sequence. Suppose we are taking the sequence x of n of length n, that is, suppose we are having 4 samples in the sequence. So capital N is equal to 4 in this case. So this will become clear when we solve the numerical on DFT. So to take the inverse, that is, we can have the inverse discrete Fourier transform equation. So this is how it is derived, but we are not expecting the derivation here. So we can directly see the formula for inverse discrete Fourier transform IDFT. So inverse discrete Fourier transform, that is, we can get the time domain representation from the frequency domain representation. So if we know the x of k, which is the DFT of a sequence, we can obtain the time domain sequence x of n by using this formula. So here notice the change in the variables. Now it is 1 upon n. What is n? N is the length of the sequence. Summation is from k equal to 0 to n minus 1. X of k denotes the DFT, and e raised to plus j 2 pi n k upon n. So here also we are using this as a basis function, but only the thing is here it is plus sign and here it is having a minus sign for case of DFT. So here in this case, here it is having a minus sign, but here in this case we are having a plus sign. So we can use this formula for computing the IDFT of a sequence. So remember these two set of formulas. One is the DFT formula x of k, and another is the IDFT formula x of n. So these two formulas will be used for solving the numericals for DFT and IDFT. So we will be given a sequence, we are asked to compute the DFT, or we may be given the DFT and we are asked to compute the IDFT. So we should know what are these different variables here. Capital N denotes the length of the sequence and the range of k is from 0 to n minus 1. Similarly here k x of k is the index which denotes the DFT, and capital N ranges from, capital N is the length of the sequence. So DFT, the notation of DFT is like this: x of n. So DFT IDFT is denoted by x of k. So remember this k variable. This k variable is actually a variable which denotes the time index for discrete time. Okay, so that's why we are using this variable k here, and n is the time index in the time domain. So k is the time index, is the frequency domain index. So x of k. Okay, so what is the effect of obtaining the DFT? One important point to note here is that when we take the finite number of samples of x of n, and we get the DTFT, and when we sample the DTFT in order to get DFT, okay, sampling in the frequency domain leads to periodic extension of x of n in the time domain. Okay, so that is one of the important thing here we will remember as we go forward, in order to see the different properties of DFT, and in order to see the computation of DFT using the direct method or using the formula method. And later on we will also see the matrix method for computation of DFT. And lastly, we will see the fast Fourier transform algorithms that are there for computing DFT. So in this unit, we will be talking about DFT, IDFT, computation of DFT and IDFT by formulas, then by matrix method, and then we will study the fast Fourier transform algorithms, which are two different algorithms: discrete DITFFT, that is decimation in time fast Fourier transform algorithm, and another algorithm is DIFFFT, which is called as decimation in frequency fast Fourier transform algorithms. Okay, so let us proceed further in the next lecture to see the numericals on DFT. Okay, thank you.